Hello students, welcome to this lecture, One Number System. So in this lecture, basically, first of all, we'll give you syllabus overview according to CBSE board. Okay, so in first chapter name is number system. Okay, and here we will cover basically real numbers, and the weightage of this chapter is 10 marks. And then second chapter is algebra. Second unit is algebra, and here we will cover polynomials, linear equation in two variables. Okay, and third unit is coordinate geometry. Here we will cover coordinate geometry. Right, that is basically introduction of coordinate geometry. Okay, and the weightage of this chapter is 4 marks. And then the next unit is geometry, and in geometry there will cover introduction to Euclid's geometry, lines and angles, triangles, quadrilaterals and circles. Okay, and this unit, geometry unit, is very important units to your according to your CBSE board. Okay, so the weightage of this chapter is 27 marks. Okay, and this is the highest weightage of this class. Okay, and then next mensuration. Okay, and then next chapter is statistics, and then next chapter is then we here internal assessment, that marks is 20 marks. Okay, so first of all, in this lecture we will cover real numbers. Okay, so let's get started. So in this lecture we will first introduce number systems. Okay, so actually what is number system and how many types of number are there that we'll here discuss. So in this lecture we shall discuss types of numbers, their number line representations, examples, and hence let us first review the types of numbers and recall the definitions. Okay, so let us first review the types of numbers. So first type of number is natural numbers. So what is natural numbers? We all know, you all count objects. Okay, like 1, 2, 3, 4, 5, 6, 7 and dot. Okay, so while counting numbers are natural numbers, and the natural number is denoted by the alphabet natural n. Okay, so if n is the set of natural numbers, then n is equal to set 1, 2, 3, 4, dot. Okay, so set of whole numbers 1, 2, 3, 4 dot. This is actually natural numbers. Okay, so now let us move to whole numbers. So what is whole number? So natural numbers including 0 represent the set of whole numbers. Okay, so if we include 0 with natural numbers, then we'll get whole numbers, and it is denoted by the symbol W. And for example, W is equal to 0, 1, 2, 3, 4 dot. Okay, so W is equal to curly brace 0, 1, 2, 3, 4 and dot curly brace close. Okay, so what is whole number? Natural number including 0 that represent the set of whole numbers. And now let us see what are integers. So integers are basically whole numbers including 0 and their negatives. Okay, so they can be represented mathematically as z is equal to curly brace dot -3, -2, -1, 0, 1, 2, 3, dot, where z is the symbol for the set of integers. Okay, so what are integers? Integers is nothing but the union of whole numbers and their negatives. Okay, so now let us move to next types of number, that is rational number. Okay, so what are rational numbers? So any number that can be expressed in the form p over q, where q does not equal to 0 and pq are integers. Okay, it's called a rational number. So any number that can be expressed in the form p over q, where q does not equal to 0 and p and q are integers, is called a rational number. Whole integers, whole recurring decimals and whole terminating decimals are rational numbers. Okay, so note it down: whole integers, whole recurring decimal and whole terminating decimals are rational numbers. Any integer can be expressed in the form p over q, where q does not equal to 0. That is why whole integers are rational numbers. Okay, so for example, 2 by 1, 3 by 1, 4 by 1, etc. are rational numbers. Okay, so now let us discuss any recurring decimal can be expressed in the form of p over q. Okay, for example, if you take 0.333 dot dot dot, so this is a recurring decimal expansion. Okay, so we can write 0.333 dot 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 is equal to 1 by 3. That means 0.333 dot dot dot. This number can be expressed in the form of p over q, where pq from integers and q does not equal to 0. Okay, and we can also write 0.1666 dot 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 is equal to 1 by 6. Okay, so any terminating decimal can be expressed in the form p over q, where q does not equal to 0. An example, 0.5, this is terminating decimal expansion of 5 by 10. Okay, so 0.5, this is equal to 5 by 10, and for this is equal to 1 by 2. And 0.25, this is equal to 25 by 100, that is equal to 1 by 4. Okay, so this type of whole terminating decimal can be expressed in the form p over q, where q does not equal to 0. And then here we'll discuss about number line. Okay, so what is number line? So a straight line, number line is nothing but a straight line, one of which points are identified with real numbers, is called a number line. Okay, successive integers are placed on the number line at regular intervals. Okay, at regular intervals, and the following is an illustration of the number line. So this is the illustration of the number line. So this is actually a straight line. Okay, one which points are identified with real numbers. Okay, so and the integers in the successive integers are placed on the number line at regular intervals. Okay, so these intervals are regular intervals and these are successive integers. Okay, and they are placed on the number line at regular intervals. So this is 0, this is 1, this is 2, and dot dot dot, and here -1, -2, and so on. So this is the illustration of the number line. So now let us represent natural numbers one number line. Okay, so how can you represent a natural number one number line? So let us see. First of all, draw a line, make a point 1 which represents 0. Okay, and now on the right hand side of 0, mark points are equal intervals of length as shown this as shown below. Okay, so here we first of all take mark a point 1 which represents 0, and then right hand side of the 0 mark points at equal intervals of length. Okay, so we take 1, 2, 3, 4 on the right hand side of 0. The 0 are equal mark points are equal intervals. These are all equal intervals of length. Okay, so these points represent natural number 1, 2, 3, 4 dot 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 respectively. the three dots on the number line indicate the continuation of these numbers indefinitely. Okay, so this must be kept on your mind. The three dots on the number line indicate the continuation of these numbers indefinitely. Okay, so now let us see how to represent this, how to represent whole numbers, one number line. So this is similar as natural number, okay, but with the inclusion of 0 in the number line, it is as follows. Okay, first of all, mark a point 1 that represent 0, and right hand side on the 0, here we take the integer, the number 1 2 3 at the equal intervals of the length. Okay, so this is the representation of whole numbers, one number line. And here three dot, this indicate the continuation of the number indefinitely. Okay, so now let us see how to represent integers. Okay, so we know integers mean what? Integers actually, the set of integers is z is equal to dot -3, -2, -1, 0, 1, 2, 3, dot. Okay, so here first of all draw a line and mark a point 1 which represents 0. Okay, so first of all we draw a line and mark a point 1 which represents 0, and then three dots on either side show of continuation of integers indefinitely on each side. Okay, and we place 1 2 3 right side on the 0. Here are equal intervals of the length, and here we place -1, -2, -3 and dot left hand side on the 0. Okay, and they are actually equal, their place equal intervals of the length. Now let us see how to represent rational number one number line. Okay, so now rational number can be represented by some points on the number line. So first of all, draw a line and mark a point 1 which represents 0. So set equal distances on both sides of 0, and each point one division represents an integer as shown below. Okay, so we made this. First of all, we draw a line, okay, and mark a point which represents 0, and we place right hand side of 0 1 2 3 4, and left hand side of the 0 -1 -2 -3 -4 and so on. Okay, and then we set the interval, set equal distances on both sides of 0. So the length between two successive integers is called unit length. Okay, so keep on your mind the length between two successive integers. That means length between 0 to 1, length between 1 to 2, length between 2 to 3, length between -1 to 0, length between -2 to -1. They are equal length, and this length is called unit length. Okay, and here if we take now 1/2, okay, so 1/2, this is a rational number. Okay, so you can place it between 0 to 1. Okay, so if somewhere here there actually we can place 1/2. Okay, so now let us move to example. So in this slide we will see example. So in this example here we have asked, are the following statements true or false? Okay, and give reasons for your answers. So in first one, here we have every whole number is a natural number. Is this correct? And then second statement, here we have given every integer is a rational number. Okay, and in third statement, here we have every rational number is an integer. Okay, so let us justify our answer. Okay, and let us see which are the following statements true or false. So first statement, every whole number is a natural number. This is false because 0 is a whole number but not a natural number. Okay, so 0, this is a whole number but not a natural number. So this is why the given statement every whole number is a natural number is a false statement. And second, every integer is a rational number. Okay, so every integer is a rational number. This statement actually true statement because every integer m can be expressed in the form m by 1 and so it is a rational number. Okay, so every integer is a rational number. This statement is a true statement. And now let us see third statement. So in third statement, here we have every rational number is an integer. Okay, so this statement actually a false statement. And why this is false statement? Because if you take 3 by 5, this is rational number but is not an integer. Okay, that is why the given statement is a false statement. And now let us see next example. So in next example, here we have to find 5 rational number between 1 and 2. Okay, so let us see how to solve it. So first of all, recall that to find a rational number between R and S, so you can add R and S and divide the sum by 2. Okay, that is R plus S by 2. This lies between R and S. So here we have 1 and 2, these two numbers. So now if we add 1 and 2, then we'll get 1 plus 2, that is equal to 3. And now if we divide it, then we'll get 3 by 2. Okay, so 3 by 2, this number is a number between 1 and 2. And you can proceed in this manner to find four more rational number between 1 and 2. Okay, and these 4 numbers are basically 5 by 4, 11 by 8, 13 by 8 and 7 by 4. Okay, so here in this process is very lengthy process. Okay, and this process is time taking process. So now let us see next let us see solution number 2. Okay, the other option is to find all the 5 rational number in one step. Okay, so the previous method is not a one step method. That was many step method. Okay, so that is not easy to find the rational number between 2 rational number, okay, in one step. So here in this solution, we will find one rational number in one step. Since we want 5 numbers and we write 1 and 2 as rational numbers with denominator 5 plus 1, that is 1 is equal to 6 by 6 and 2 is equal to 12 by 6. Then you can check that 7 by 6, 8 by 6, 9 by 6 and 11 by 6 are one rational number between 1 and 2. So the 5 numbers are that lies between 1 and 2, and rational number also that are 7 by 6, 4 by 3, 3 by 2, 5 by 3 and 11 by 6. Okay, so now let us see one remark. So notice that in example number 2, here you were asked to find 5 rational number between 1 and 2. But you must have realized that in fact there are infinitely many rational number between 1 and 2. Okay, so in general there are infinitely many rational number between any two given rational number. Okay, so notice that in example 2 there are infinitely many rational number between any given rational numbers. Okay, and then then let us take a look at the number line again. Okay, so have you picked up all the numbers? Okay, so have you picked up all the numbers? The answer is not yet. Okay, the fact is that there are infinitely many more numbers left on the number line. Okay, infinitely many more numbers left on the number line. There are gaps in between the places of the numbers you pick up, and not just one or two, but infinitely many. Okay, the amazing thing is that there are infinitely many numbers lying between any two of these gaps too. Okay, so we were left with the following questions. But their first question is, what are the numbers that are left on the number line? Okay, this is first question. And second question is, how do we recognize them? And that is, how do we distinguish them from the rational number? Okay, so these questions will be answered in the next section. So these questions will answer in the next section. So let us see next section. Okay, so in next section here we will discuss about irrational number. Okay, so we saw in the previous section that there may be numbers on the number line that are not rationals. Okay, so in this section we are going to investigate these numbers so far. Well, the numbers you have come across are of the form P over Q, where P and Q are integers and Q does not equal to 0. So you may ask, are there numbers which are not in the form? There are indeed such numbers. Okay, there are indeed such numbers. Okay, so we saw in this previous section that there may be numbers on the number line that are not rationals, and in this section basically we will investigate about these numbers. Okay, so let us see the Pythagoras. The name, about the philosopher Pythagoras. Okay, famous mathematician, was Greece famous mathematician. Okay, so the Pythagoreans in Greece, followers of famous mathematician and philosopher Pythagoras, were the first to discover the numbers which were not irrational, which were not rationals. Okay, around 400 BC, before Christ. These numbers are called irrational numbers. Okay, irrationals because they cannot be written in the form of a ratio of integers. Okay, there are many myths surrounding the discovery of irrational number by the Pythagoreans. So Hipparchus of Croton involved the myths. Hipparchus has an unfortunate end for discovering that root 2 is irrational for disclosing the secret about root 2 to people outside the sacred Pythagorean sect. Okay, so he is the famous great mathematician Pythagoras. Okay, so let us now formally define these numbers. So a number is called irrational if it cannot be written in the form P over Q, where P and Q are integer and Q does not equal to 0. So you already know that these are infinitely many. There are infinitely many rational numbers on the number line. Okay, so it turns out that there are infinitely many irrational numbers on number line 2. So some examples of irrational number are root 2, root 3, root 5, root 15, 5, 0.10111011 dot. Okay, this is non-terminating decimal. Okay, so this type of numbers are called irrational numbers. So now let us see remark. So recall that when we use the symbol square root, we assume that it is the positive square root of the number. Okay, so square root 4, that is equal to 2, though both 2 and minus 2 are square roots of 4. Okay, but we take only square root 4, this is equal to 2. Some of irrational number listed above are familiar to you. So you are familiar to with root 2, root 3, pi. Okay. So for example, if you now if you have already come across many of these square roots listed above and the number pi. Okay. So you have already come across many of the square roots listed above and the number pi. So the Pythagoreans proved that root 2 is irrational. Later in approximately 425 before Christ, Theodorus of Cyrene showed that root 3, root 5, root 6, root 7, root 11, root 12, root 13, root 14, root 15 and root 17 are also irrationals. So proof of irrationality of root 2, root 3, root 5, etc. shall be discussed in class 10th. Okay, as to pi, it was known to various cultures for thousands of years. So it was proved to be irrational by Lambert and Legendary only in the late 70s. So in the next solution, we will discuss why 0.1011011101110 and dot and pi are irrational. Okay. So let us return to the questions raised at the end of the previous section. Here remember the bag of rational numbers. Okay, and if we now put one irrational number into the bag, will there be any number left on the number line? Okay, so the answer is no. Okay, so it turns out that the collection of rational number and irrational number together make up what we call the collection of real numbers. Okay, so if we take together rational numbers and irrational number, then we'll get actually collection of real numbers. Okay, so which is denoted by bold R. Okay, and therefore our real number is either rational number or irrational number. So we can say that every real number is represented by a unique point on the number line. Also, every point on the number line represents a unique real number. So this is why we call the number line the real number line. Okay, so here we give reason why number line is called real number line. Okay, so because every point on the number line represents a unique real number, that is why the call the number line the real number line. Okay, so now in the 1870s, two German mathematicians, Cantor and Dedekind, showed that corresponding to every real numbers there is a point on the real number line, and corresponding to every point on the number line there exists a unique real number R, okay, R Dedekind. So is great mathematician G. Cantor. Okay, so let us see how we can locate some of the irrational number on the number line. Okay, so in our next section we will see how to represent irrational number on the number line. Okay, so for clearing our concept here, first of all we will discuss example. So in this example here we have to locate root 2 on the number line. Okay, so how can we locate root 2 on the number line? So let us see how to locate root 2 on the number line. Okay, so it is easy to see how the Greeks might have discovered root 2. Okay, consider a square OABC with each side 1 unit in length. That is shown in figure 1.6. So then you can see by the Pythagorean theorem that OB OB, this is equal to square root of 1 square plus 1 square, and this is equal to square root of 2. So how do we represent root 2 on the number line? So let us see now how to represent root 2 on the number line. So here this is figure number 1.6. So in this figure here, ABCO, this is actually a square and with side 1. Okay, so then this diagonal this is actually equal to root 2 by Pythagoras theorem. So this is easy. Transfer figure 1.6 to the number line, making sure that the vertex O coincide with 0. Okay, so now let us see figure number 1.7. So in this figure, now we place this square on the number line. Okay, so we have just seen that OB, this is equal to root 2. Okay, and now if we using compass with center O and radius OB and draw an arc that intersecting the number line at the point P. Okay, so then P corresponds to root 2 on the number line. Okay, so this point P actually represent the number root 2 on the number line. Okay, so now let us see how to locate root 3 on the number line. Okay, so now let us discuss how to locate root 3 on the number line. So let us return to the figure 1.7. Okay, so if we return to the figure 1.7, so then now here you can take like this. Okay, so this is OB is equal to root 2, and here we join DB and DO, and here this length is 1, and then by Pythagoras theorem, one triangle, right triangle OBD, here this angle is 90 degree. Okay, then this is actually square root of root 2 square plus 1 square, that is equal to root 3. Okay, so this OD is actually root 3. So now if we now draw an arc with center O and radius OD, then it will intersecting number line at point Q. Okay, so this Q represents root 3 here. And now here actually given detailed explanation. Here first of all, construct BD of unit length perpendicular to OB. Okay, that is shown in this figure. Okay, so then using the Pythagoras theorem, we see that OD is equal to square root of root 2 square plus 1 square, that is equal to root 3. And using a compass with center O and radius OD, draw an arc which intersects the number line at the point Q. Okay, then Q corresponds to root 3. So in the same manner and in the same way, you can locate root n for any positive integer n after root over n minus 1 has been located. So I stop here this lecture. Thank you very much to all of you.